Hello, everyone. My name is Shaz Balahi. I'm a senior here at UC Davis studying mechanical engineering.
I'm Austin Wu. I'm a junior studying mechanical and aerospace engineering.
I'm Ramon Becerrosco. I'm a freshman studying aerospace engineering.
And I'm Raul Duarte, a first year electrical engineering student.
And today we're going to be discussing our research on the development of low-cost photodiode sun sensors for CubeSat Attitude Determination. So what sun sensors are basically one of the most commonly used devices for satellite attitude determination. And what that means is figuring out how a satellite is oriented in space. And commercially available sun sensors can be bought for a couple $1,000s, which means undergraduate students can't access that for their own research application. So what we're doing is using inexpensive semiconductor devices called photodiodes, which cost around $1 to $1.50 per diode, to provide an economical means of satellite attitude determination. And the first objective of this research is to create working sun sensors for the REALOP CubeSat, which is going to be the first CubeSat created by undergraduate students at UC Davis. And then secondly, we're trying to document this in as much detail as possible so that students around the world, when they need to create their own budget sun sensors, they can kind of reference our documentation and it'll make it a lot easier for them. So before getting into the details of the testing methodology, I'll talk a little bit about the basic principle by which photodiodes can be used as sun sensors. So shown here in figure 2, a light ray that strikes normal to the surface of the diode, that is theta equals 0 degrees, will achieve a maximum intensity of I naught, and therefore a maximum voltage output of V naught. As this angle theta increases, the voltage output decreases with the cosine of the angle. In other words, it becomes a fraction of the V naught value. And this concept is captured by these equations shown here. And this is the basic principle by which we can use to figure out how our satellite is oriented in space. And the specific photodiode that we're using for testing is called the Osram SFH2430. It basically fits the bill for our application. It has a wide temperature operating range, good response time, and a successful spaceflight heritage aboard other university CubeSats. And to test it, we created this resistor capacitive circuit shown here in figure 1. It's an active low-pass circuit used in conjunction with an Arduino microcontroller, which allows us to do a couple of things. So the filter cleans up the signal. The operational amplifiers amplify the photodiode's undetectably small voltage output so that the Arduino can measure and record the voltage outputs. And then we've also constructed a test bed shown here in figure 3. It's a wooden Mach 1U CubeSat called WoodSat. And what this test bed does is help us calibrate the sensors and identify the optimal configuration that will meet the pointing requirements of the satellite. And WoodSat has 5 faces available for mounting photodiodes, either flat onto the face of the satellite or in pyramidal clusters of 4 photodiodes each. And it can also rotate about 3 axes. So to conduct a test, first we mount the photodiodes in the desired configuration, and then we fix a light source directly above the satellite. And the types of light sources we've used so far include LED, ultraviolet, and infrared bulbs. And this is intended to capture different parts of the sun's electromagnetic spectrum. And then after mounting the light source and the photodiodes, we rotate the satellite to some known orientations while the respective voltage output is recorded. And there's a couple of different configurations that we're using for testing. So far we've done a single axis test with either a single diode mounted on one face or a single pyramid cluster mounted on one face, as well as 3 axis test with either a diode on each face or a pyramid cluster on each face. And for the single axis test, we rotate the CubeSat from 0 to 90 degrees in 5-degree increments, and at each increment, we record the voltage output. The 3 axis tests, which are currently underway, we rotate the CubeSat about each axis to some predetermined Euler angles. And then we use the voltage outputs from the sensors on each face and we match them to the theoretical angle. And that is then resolved to the light vector, since each voltage corresponds to some unique angle. And by this method, we can characterize the error by comparison with the known orientation. So now Ray is going to talk a little bit about the design of the pyramid as well as the results from our testing.
Thanks, Shazib. To start off, we have a design in the top right, which is a preliminary design in the that was using the 1U mock CubeSat test I mentioned earlier. Now on the bottom here, we have the latest design for the actual CubeSat. Each of the photodiodes here will have a 30-degree incline to take into account the photodiode's conical field of view. And as you can see in the top left illustration, it shows how the 60-degree half angle provided by the 30-degree incline gives the pyramid full coverage of light. Continuing on, we have some changes in integration on electrical components as well as protecting against radiation. To account for the high levels of radiation in the low Earth orbit, we will be putting protective cover glass on top of each photodiode. The photodiodes will be attached onto miniature PCBs, which on each face of the pyramid. And additionally, the pyramid itself would be attached onto a larger PCB that would be on the face of the satellite, allowing vertical pins to make contact with the mini ones and the larger PCBs. Here we have some results from testing the sun sensor voltage readings through different light sources. The results state that the lowest peak voltage was produced by ultraviolet, followed by infrared. To account for the different peak voltages from each light source, the data was normalized by dividing by the peak voltage. Some things we considered that would account for error in our testing was ambient light coming from the Arduino and laptops, the color of the pyramid not being a dark color, and also a big factor in some test scenarios was budgetary restraints. If we wanted to test this under ideal conditions, we would have to get our hands on a solar simulator and be able to collimate our light sources. And now here's Austin for data analysis.
Using the average normalized results, the percent error between the test results and the expected cosine relation values were found. From the error plots, we found that the sun sensors performed best in the visible light range of wavelengths under LED light. That the sun sensors had increased error as the angle of incidence increased, and that the pyramid design was able to significantly decrease the error in sensor readings. The datasheet on the photodiodes show that the range of wavelengths in which the photodiodes have a sensitivity of 50% and higher was between 500 and 700 nanometers, which is mostly in the visible light range. We observed this behavior when the voltage readings from the UV and IR were lower than the readings under LED. Although the error plots show that under UV and IR, the sensors were closer to the cosine relation, IR had a large range of error beyond 100% and 100% for the pyramid and double that for the flat sensor. Sensors under the UV condition provided varied data sets compared to LED and IR, but was not noticeable when the sets were averaged out. Because of these observations, the results from UV and IR conditions present the effect of noise that the sensors could detect during flight, while the LED conditions present the ideal sun sensor behavior during actual space flight. Looking at the percentage error plots of the sensors in LED light, we can see that the pyramid sensor was able to reduce the amount of error compared to the flat sun sensor. The flat sun sensor data shows that the error increases as the angle of incidence increased. Past the 60 degrees, which is the half angle of the photodiode, the rate of increase increases slightly, as we can see in this plot. The pyramid results, on the other hand, show a decrease in the error past the 60 degrees angle, suggesting that the design was able to overcome the field of view limitation that the photodiodes had. Although both designs in general had an increase in error as the angle of incidence increases, we can reduce this error from this source in the satellite determination algorithm. Now Raul will talk about our conclusions.
Right. Thank you, Austin. All right, so the Space and Satellites Club conducted this research to determine the necessity of using the pyramid versus the flat sun sensor configuration. An accurate sun sensor system is necessary to determine our orientation relative to the Earth and to make any necessary adjustments to the satellite. As our main determination system, it is critical that the system be as accurate as possible. With this objective in mind, the conclusion is clear. Based on the large difference in error between the flat design and the pyramid design, with the latter approaching 50% in some test beds, we have chosen to use the pyramid design in our sun sensor system. For future plans, we have to optimize the angle determination vector algorithm, adjusting for dark current, and reduce the overall error. Even the 7.866% error that we currently have for our pyramid configuration on average is unacceptable. We need to conduct more tests and reduce sources of error by, for example, painting the testing rig black, turning off or dimming monitors, and covering the Arduino light as mentioned before. We need to test our photodiodes with the quad operational amplifiers they will be using on the CubeSat in order to minimize the error occurring from the change in components. Finally, we need to determine if the protective glass we will be using on the satellites will have a differentiable impact on the measurements or the error in angle determination.
And that concludes our presentation. We'd like to thank Professor Robinson, Kylie Cooper, Abe Nagy, and Corey George for their continued support in conducting this research, as well as the rest of the Sun Sensors team for their contributions to this project. And thank you so much for watching.